So welcome everybody to another session of Lógicos in Quarentena. On behalf of the Brazilian Logic Society and of the Logic Interest Group of the Brazilian Computer Society, I'd like to thank very much Professor Martin Escardo, who kindly accepted our invitation to give this talk. Martin, thank you very much.
I'm going to say my acknowledgements in Portuguese and then I'll give my talk in English. Obrigado, Bruno, por me convidar. É prazer dar uma palestra no Brasil, de longe, pelo menos. So now I'm going to start. Thanks a lot. So I want to talk about univalent foundations and homotopy type theory and Martin-Lev type theory, but I'm not going to assume any background on this subject. I'm going to try to introduce everything from scratch, and the main focus here will be on the notion of equality. If I manage to move to the next screen here. Here we go. So if you do mathematics, then of course you consider two groups to be the same if they are isomorphic. And for example, you say the free group on one generator, and this is the integers. And similarly, we say, well, two topological spaces are supposed to be the same if they are homeomorphic, and metric spaces if they are isometric, and categories if they are equivalent, and so on, right? So you're very familiar with that. And so it is naturally to ask the following. So do we choose these notions of identification or of sameness motivated by particular mathematical applications, or there is nothing we can do about it, so these notions of sameness are imposed upon us? Yeah, so that's a similarly philosophical question, but actually there is a mathematical answer. So if we work in a foundation different from set theory, so this you wouldn't be able to do this in set theory, but if you work in Martin-Lev type theory, and we use the notion of equality, which is known as the identity type. And we use an axiom, which is called the Univalence Axiom, which was proposed by Vladimir Voevodsky. Then we can actually prove that equality of groups is isomorphism, equality of topological spaces is homeomorphism, and so on. Equality of categories is equivalence. So yeah, it's very nice because you have a single axiom, the Univalence axiom, and then a notion of the identity type that comes with Martin-Lev type theory. And then we can then we don't have any more as definitions these notions of sameness. They become theorems. So these are theorems. So in this talk, I want to explain a little bit how this works. But before we start explaining how this works, we have to give a warning. The warning is the following: sometimes we actually do regard two groups to be the same if and only if they have the same elements. So one example that you may or may not know, it doesn't matter much, but it's an example that occurs in practice in mathematics. So if you take a group, fix a group, and now look at all the subgroups and order them by inclusion, they form a lattice, but also this lattice is algebraic, so it has some further properties. And then the compact elements of this algebraic lattice are the finitely generated subgroups. So that's a classical theorem. Now, if you identify isomorphic subgroups, this example doesn't work. So you cannot identify two different groups if you want this theorem to be true, if they are isomorphic. Okay, So we seem to be choosing a different notion of identification according to applications. Yeah, but actually, I want to show that this is not the case, at least not in type theory. So in type theory, we have the type of groups. So I'm going to write it GRP. And now if you have two groups in this type of groups, it will turn out that, so if I call this the identity type that I mentioned before, this is the same thing as isomorphism of groups. That's the type of groups. But in the second example, where we saw that something was failing, actually we have a different type. So now you have a group here in the type of groups. We can form another type, the type of subgroups of G. And you can take two subgroups of G there. And the situation will be a little bit different from what we had here. Actually, it will be completely different. So the situation we're going to have is that in the sense of the identity type, the identity type actually is characterized in the way you would think. So for every element of G, we have that X is an element of H if and only if it is an element of H prime. So why is this happening here? Well, the reason this is happening is that equality in Martin-Lev type theory is not global. So each type, and here is a type, and here is another type. So each type has its own equality. So the equality is actually defined in the same way for all types, but it behaves differently in the types according to the way you define the types. Okay, so this is what I want to explain in this talk. So how we define equality in a uniform way for all types, and how we can define different types, for example, this one or this one and many others. I have lots of examples in this talk and the slides, but I'm not sure how many of them will make it through to the talk. Please stop me at any time you want with questions. I don't mind at all being interrupted, okay? So just interrupt me. I'll be very happy to answer. So,
Martin,
yes.
Petruccio here. I have a small doubt.
Yes.
It is about the first square, the first rectangle that you draw here. Is this a consequence of the axiom, or this is a consequence of Martin-Lev type theory? I mean, do you need the axiom or not to have that?
You need the axiom, but it's also a consequence of Martin-Lev type theory, because I'm going to explain this in another slide. But for now, the answer is you need both the axiom and Martin-Lev notions of identity type. Yeah, that's okay. A good question, actually, which I'll try to explain a little bit more later.
Okay, thank you.
Okay, so what I'm going to use in this talk is a so-called structure identity principle. It has some history. So the first class of theorems for this was proved for algebraic structures, for a large class of algebraic structures. Then for objects of categories, this is in the HoTT book. I think it was formulated first by Peter Axel, and then it was proved by Arens, Kapulkin, and Schulman. It's also in the homotopy type theory book. I proved a different way, a different structure identity principle, which we are going to use in this talk in my lecture notes on univalent type theory or univalent foundations of mathematics. So what is new in what I'm going to talk about now is a general theorem that can be applied for groups, for topological spaces, for categories, and many other things. And also, it can be applied in a modular way. So for example, if you have a group and then you add more structure to the group so that it becomes a ring, then you can actually combine two theorems about each of the two structures to get a combined result. I'm going to be more precise about this later. And then there is a later version by these four people, Arens, North, Schulman, and Semensis, which actually works for higher structures, you know, like higher categories and things like that. But I'm not going to get there in this talk. As I said before, I don't expect you to be familiar with Martin-Lev type theory, but I'm actually not going to explain it and then give the talk. I'm instead going to explain it as we go. So if you have any doubts, please stop me, okay? Before I explain Martin-Lev type theory, so let's see what is going on here. So as you know, Martin-Lev type theory, as you probably know, Martin-Lev type theory was invented originally as a foundation of classical mathematics, yeah? Sorry, constructive mathematics. And so it's a little bit strange that a classical mathematician such as Voevodsky started from something like this to do his mathematics. But actually, it was exactly what he needed, yeah? So what's going to happen in univalent type theory, we start from one, and then the types are going to generalize sets. It's better to give this by example. So typical example of sets will be the natural numbers, the integers, the rationals, the real numbers, the complex numbers. And we don't actually stipulate that they are sets. It's actually, we prove that they are sets. We just define them in the usual way, and then we prove that they are sets. So now, what does it mean to be a set? Well, it is not the same thing as in set theory that you have the distinction between set and class. So it's not about that. It is about it's about the equality type or the identity type. So in the example I gave you, we had that the identity type of two groups was the type of isomorphisms. Now, what this means now is that now two groups can actually be equal in more than one way, because if you have two different isomorphisms between the same two groups, there will be, so you have several isomorphisms here, which means you will have several equalities here, each equality corresponding to an isomorphism. So we say a type is a set if there is at most one way for things to be equal. So an example would be the natural number. So there is at most one way for 17 to be equal to 17, like exactly one actually, and there are no ways for 0 to be equal to 1. So these types are sets because there is only one way for them, at most one way for them to be equal. Now the type of groups actually will be it will be called the so-called one groupoid. I can try to explain this later, but what this really means is that if you draw a picture of the type, so here we have two groups and we write arrows for the equalities, so there can be several equalities. But you can, in a more complicated case, like in the case of categories. So let's say you have a category here and a category here. Now the equalities are going to be in one-to-one correspondence with the equivalences of categories. But now it turns out that you can compare equivalences. So you can ask whether two equivalences are equal, and then this is non-trivial. That's why it is a two-groupoid. And in some other examples, can be more complicated. They can be 3 groupoids. So you can compare the elements of the type. You can compare the comparisons. And then you can compare the comparisons of the comparisons. And that will be something like a 3 groupoid. So I'm going to give a more mathematical definition later, but the pictures are like that. And this is why Voevodsky wanted to do this business, because he wanted, in homotopy, this kind of structures arise in homotopy theory, and he wanted to have a formalization, a foundation, which could more directly formalize infinity categories and homotopy theory. But I'm not going in this talk to talk about homotopy theory or infinity categories. I'm going to do examples which are simpler, like these ones and the sets. So for example, the type of sets is a 1 groupoid, the type of rings and posets is a 1 groupoid. You may be a little bit surprised, the type of well-ordered sets, which has the same pattern as this, actually turns out to be a 0 groupoid, or actually a set. It doesn't have higher structure like these ones. I pose an exercise to the audience. Think about why this could be the case as I give the precise definition later, and maybe somebody can tell me why we have 0 rather than 1 in the type of ordinals. In the case of categories, I already explained. But I'll give you this as an exercise for you to think during the talk. Okay, so let me try to be a little bit quicker here. So I'm just going to emphasize what I said before. The distinction between a type being a set and not a set is not about it being small or large. So here's an example. So all the 4 possible combinations actually exist. So the type of natural numbers or the type of functions is both small and a set. Then there are types which are small but not sets. One of them is the homotopical circle, which I'm not going to discuss in this lecture. And then the type of ordinals is both large and a set. And then let's see. The type of sets, the type of types, the type of magmas, they are large and they are not sets. So all the 4 possible combinations are possible. Yeah. So set versus not set doesn't have anything to do with size. It has to do with the complexity of equality, as in the picture that I did before. Okay, so let's start by one concrete example. So we say that a magma is a set equipped with a binary operation. We write it like multiplication, and then there are no axioms, no laws. So in set theory, a magma is simply a pair. So it's a set and the operation. But in univalent type theory, as we discussed, not all types are sets. So we need to give this information. So now the magma is going to be a triple. So it's going to be the type again. Now the information that we require in this type to be a set, and the binary operation. So it's going to be a triple. And we collect all these triples in a single type, and I'm going to call it magma. So for example, we're going to write that this triple here is in the type magma. So how can we define magma in type theory? Well, we need 2 ingredients. So one is we need a type universe, and the second ingredient is the so-called sigma type. So let's discuss the universe first. So if you take all the small types, this would include the natural numbers, the real numbers, and many other types, they are going to form a large type. So we give a name U, and we call this type a universe. Yeah. And for our discussion, it is important that all types have a notion of identity type or equality. including the universe, yeah? So the universe has to be a genuine type. It's going to be a large type, but it's going to be, apart from the distinction of size, it will have the same properties as all the other types. So now, formally, a magma is going to be a triple, where the first component is in the universe of types. The second component is the information that X is a set. Actually, later I'm going to give a definition of this. Later we give a definition of what it means to be a set. And an operation, yeah? So the way to form pairs and triples and things like that in Martin-Lev type theory is to use this sigma type. So sigma type is like the Cartesian product. So here we have a Cartesian product. So let's look at this definition carefully. So we look at it from inside here. So we have this Cartesian product, and this corresponds to this part here. And now the sigma type is a little bit like the Cartesian product in that is a type of pairs. So here is the first element, and here is the second element of the pair. But what happens is that the second component, so the second component here, can refer to the first component. And you notice here, let me use another color to emphasize this. Okay, let's choose this color. So the second component, which has these two things here, so here it is actually, the second component, it refers to the first component. So this is an example of a dependent type, yeah? So you first give something which is an element of the universe, and then you give something else in the second component which depends on the first type. But other than that, it's just like a Cartesian product to form pairs, and if you iterate this, then you get triples here. Yeah. Any question about that if you haven't seen this before? Okay.
Yeah. Hi, Martin. Sorry about being late, but why do we have? Why do we kind of think about the product of the magma as kind of being? We don't have to say. Why don't we have anything that we say about that? And how do I think about the fact that I have you have to have this Cartesian product there, right?
Okay, so so the sigma type is just a formalization of what we have already written here, right? So you shouldn't interpret the sigma type exactly as in this informal definition. So the formalization by sigma corresponds exactly to this informal statement. So a magma is a triple, where the first component is this, or you can say a magma is a pair, if you can write a bracket here. Yeah. This is the first component here, and now the second component is this other pair. What is happening is that the second component is referring to the first component. So the second component is using X again. Yeah.
Right.
So
but
that's
it's also using the Cartesian product. That's the thing that I'm thinking it comes from nowhere there, right? It's kind of
okay. The Cartesian product is a special case of the sigma type, actually, where the second second component now doesn't depend on the first. So this operation here, this operation multiplication is not making reference to this. Yeah. So so this Cartesian product is a special case of the sigma type that you can write like this. Yeah, but that's a more technical point that I wanted to avoid, but I didn't manage. I had to explain it.
Sorry about that.
Okay. Yeah, I want to avoid as many technical points, but don't be afraid to ask about the technical points that I avoided if you want to know about them, okay? Like Valeria. So, yeah, so as I said here, right, Valeria, so sigma generalizes the Cartesian product, but you can read this the other way. The Cartesian product is a special case of sigma, yeah? And this is what happens formally here. Okay, so what we are going to have in telegraphic summary is that two magmas are equal, well, in univalent type theory, if and only if they are isomorphic. This is true, but it's very misleading because if and only if is an implication, right? So two magmas, A and B, are going to be equal if and only if they are isomorphic. Sorry. But actually, we have much more than that. We have more than that. So it's very misleading to say if and only if there. And if and only if is not enough. We want more than that. Yeah, so I say that this is imprecise but misleadingly true. So this is going to be a theorem of univalent type theory. And you can ask yourself, well, all that I did here can actually be defined in Martin-Lev type theory. We can define the type of magmas, and then we have this, and then we can ask whether this is true or not in Martin-Lev type theory. And actually, it is independent. Yeah. So this is independent of Martin-Lev type theory. So Martin-Lev type theory cannot prove or disprove that. But the univalence axiom is consistent with Martin-Lev type theory, and it implies, so the univalence axiom implies this thing here. Any question about this? Okay,
Yes.
so I'll carry on. Okay.
And I have a question, a small question. Naively,
Sure.
we think that the implication from left to right should be trivial. Is that true in this context?
Yeah. So the implication from left to right is trivial. Yes. The interesting thing is from right to
the
left.
real result is the implication from right to left. That's the
Yes.
case.
Yes.
Okay.
That's correct. Okay, so now equality of sets is very easy, or maybe it's not easy, but you're all used to it by now in your careers. Two sets are equal if they have the same elements. However, this is not possible in type theory because type theory is set up in such a way, Martin-Lev type theory is set up in such a way that given something, you cannot ask whether it is in this type and in this type. Yeah. So being an element of a type is not something that is true or false. It's a so-called judgment. And what this means in practice is that when you build a type, like the natural numbers, you create new elements that were not in any other type. So the type of natural numbers has freshly new elements for it. So you cannot have the same definition as in a set theory. And so Martin-Lev came up with the following idea. So if you fix a type X and fix 2 points of this type X, he stipulated that there is a new type, the identity type connecting X and Y, and which collects the ways in which these points are identified. So this is a type, so it's a collection. Now, Martin-Lev wanted this type actually to have at most one element. So it collects the ways, but according to his thinking, there should be at most one way of identifying two things. But this actually failed because this cannot be proved in Martin left-type theory, even though he and other people hoped that this would be the case. In fact, once you postulate the univalence axiom, this type can have many elements. Including infinitely many elements sometimes. So this is one part of the specification. The other part of the specification is that we stipulate that if these 2 points x and y are the same, then there is at least one identification, which is called REFL for reflexivity. Yeah, so you stipulate that this is an identity type. There is at least one element of these things. And now, the final thing you require is some kind of initiality. So intuitively, and it's almost correct, but not quite correct. Intuitively, you could say that the identity type is the least or smallest reflexive relation. Yeah, so you look at all the relations on the type X, and the smallest one, which is reflexive, would be the identity type. So that's not quite precise. So we have to do it in a more almost categorical way. So what we're going to do is we're going to compare this relation and this data here, this datum here, with other possibilities. So we're going to say, okay, so we have this data, which is a relation. And the way we imagine this relation is as a function, yeah? So we imagine that ID x, y is a function that takes 2 arguments and returns and gives as a value a type. Yeah, so this is a type in the universe of types. So we're going to see it like this. And the second thing is we have a function, and so the pi here is similar to the sigma. So it's a function which maps any x in this, any point of x, any little x in x, to an element of this type. Yeah. So this is called a dependent function. So this is the argument of the function, and this is the value of the function. So the argument is a point of x, and the value is such an identity type. So basically saying, given any point, you can find an element of the identity type which identifies it with itself. Okay, so this is what we discussed in the last page, except that now I added the pi type. Now we try to compare this with another candidate. So here is the so for identity, we consider another candidate with the same shape, so the same thing. And now in place of REFL, we are going to have another candidate, which so imagine A as a binary relation, yeah, binary relation. But now it is not truth valued, so it's not truth valued. Instead, it is type valued. Yeah, and why it is type valued? This is to account for the fact that you can identify the same thing in more than one ways. Yeah, like in the examples I gave before. So it's a type valued binary relation. So this is, remember, U is the type, is the large type of small types. And so now we want to say that if you're given this data here, then we have a function that maps the first one to the alternative one. Yeah, and so the input of this function, well, there are actually 3 inputs. So this is the first argument of the function. second argument of the function, and you can think of this as the third argument of the function. Yeah, so it will map this triple here, x, x, and the identification that relates x to itself to, well, to the alternative candidate of reflex. Yeah. So notice we're using a function here, and this is related to the fact that I said intuitively the identity type is the least reflexive relation. So given any other reflexive relation, it is smaller. But instead of saying smaller, we say that there is a function that maps the given data to the new data. So this sometimes is called the recursion principle, although there is no circularity here. It's just that there's a pattern of definitions in Martin Left-type theory which are called recursion and induction principles. You can actually prove later that H is the unique function with this property, but I'm not going to try to show this. Yeah. So this is the so-called the recursion principle. For most applications, the recursion principle is enough. Not for all. We're going to have examples for which it is not enough, and you need something more general, which is the induction principle. So the induction principle, we give the data A, capital A and lowercase a, in a form which is a little bit more general, and this is called the induction principle, this generalized version. So before you look at the types of these functions, actually look at an example. So usually an induction principle tells you how to prove things for all elements of some type. So if you want to prove that the property holds for all natural numbers, you prove it for 0, and then you prove that if it holds for n, it holds for the successor of n. And if you did that, then you prove it holds for every n. So now you can ask the same question, is when can I prove that a property of identifications, so think of A as a property of identifications. And but it is not any property. In the classical sense, is actually type valued. Yeah, it's type valued property rather than truth valued. So, and the induction principle tells you the following: if you want to prove that for every 2 points in the type X and for any identification P between these 2 points, the property holds, what do you need to do? Well, it says you need to prove this. Yeah, so that's the base case, or that's actually the base. That's the base case and the induction step, if you like. So this is what you need to prove, that something holds for all identifications. So if you want to prove that for all identifications something holds, you need to prove that it's enough to prove that for any point X, the property holds for X and itself with the particular identification here. Yeah, so this is kind of magic, because it says to prove something for all identifications, you need to prove this for a particular one. Now, we have at least one category theorist in the audience. We may have more, but so what does this sound familiar to you in category theory, this fact? Again?
Yoneda.
Yoneda lemma, yeah? So the Yoneda lemma says if you want to do something with all natural transformations, it is enough to know what you do to the identity natural transformation, yeah? You don't, okay, so it's a kind of magic, and this similar magic is happening here. To prove that something holds for all identifications, it is enough to prove that it holds for the reflexive identification. And actually, this is not just an analogy with the Yoneda lemma. When you make mathematical models of univalent type theory, when you interpret the identity type, you actually end up using the Yoneda lemma. Yeah, so so it is not entirely magic, entirely disconnected. Okay.
But one question there. The
Yes.
reflexive thing. Isn't that identity again? I'm sorry, it's too noisy.
Well, if it were a function, it would be the identity function, yeah? But it is not a function. It is just something that we call an identification, yeah? Some people sometimes call this a path rather than an identification. That's the modern terminology. So that would be the identity path. Yeah, you could call it like that. It does behave like some kind of identity. We're going to see this later, actually. Yeah.
Thank you.
And okay, so the data to define this function h was the function a. Sorry, the binary relation a, and the proof that it is, or the witness that it is reflexive. And then from this data, you can form a new function h, and we're going to call this function h. We're going to write it j, capital J, AA. So that's the terminology that Martin Leff used, I think, presumably because in Swedish, the word for identity begins with the letter J. I'm not absolutely sure, but I think it might be. Okay, so let's see the summary. So to specify the identity type, you have to give a type value, the quality relation, a witness that it is reflexive, and then the induction principle J. Okay, now using J, we can prove that the usual properties, so that the quality is symmetric, transitive, you can substitute equals for equals, and etc. Yeah, so you can prove the usual things about equality. We can ask again the same question: why didn't we axiomatize equality just as in set theory? Well, I discussed that because you cannot actually write down the definition of set theory. It doesn't make sense. It is not well formed syntactically. It doesn't make sense. Okay, I notice now, looking at the clock, that I have already used 45 minutes. So I'm a little bit behind schedule if you wanted me to finish in 40 minutes. Can I speak a little bit more, Bruno?
Sure. Up to you.
Well, I guess it's not just Bruno, the rest of the audience. So I carry on speaking until people start throwing tomatoes at me from your computer. Okay, so now it's the crucial thing that we have here. So if you assume univalence, which I haven't explained yet. We are going to have a following theorem. So first, we need a definition. So we are going to define a new type. We are going to call it iso AB, and AB are magmas. So I'm going to form the type of pairs something like F, and then maybe you can call it I. So this is going to be a type of pairs, and the first component of the pair is going to be a function F, and the second component of the type is going to be a witness that this F is an isomorphism. We haven't defined it formally yet, but you can imagine what the definition is. And the point is that this is not the statement that A and B are isomorphic. Actually, this collects all isomorphisms, all the possible isomorphisms between the two magmas. This type can be empty, or it can have one element, or two elements, or infinitely many elements, depending on the magmas A and B. Yeah? And now, what happens is that if we look at the identity type, the one that we were discussing before, identity type here, but now the type X is the type of magmas, and the 2 points X and Y are the magmas A and B. So this type actually is in bijection with the type of isomorphisms. So for each possible magma isomorphism, there is an element of the identity type corresponding to it uniquely. So there's a canonical bijection. And coming back to what Valeria was asking before in connection with the unity lemma, what this canonical bijection does, it maps the reflexive identification to the identity isomorphism. So I could say to Valeria, yes, actually, morally, the reflexive identification is the identity, at least in this example and many examples like this. It is a name. You can consider it as a label for the identity function. Okay. So notice that when we define the type of magmas, we didn't say what a magma isomorphism, homomorphism is, yeah? So remember the definition of magma. Let's see if we find it. So this is the definition of magma. The definition of magma is only that. But now we have a theorem saying that actually the identifications of magmas are in bijection with all the possible isomorphisms. So this is kind of, I regard this as a kind of magic, because you define the type, you didn't say what a homomorphism was, but a sort of univalent type theory knows what an isomorphism should be automatically, yeah? So somehow magically, Martin-Lev type theory with univalence knows, without we having to tell it, what a magma isomorphism has to be for this theorem to be true. So what happens, I think, from a categorical point of view is that we are defining the type of objects only, so the magmas, and then univalence automatically tells you what the isomorphisms are. It doesn't tell you what the homomorphisms are, but it tells you what the isomorphisms are. So it doesn't tell you what the homomorphisms are. But now this comes back to the question that Petruccio made at the beginning of the talk. So is this happening because of univalence only? Well, no, not only because of univalence. It is happening because of univalence, yes, but also without this definition of the identity type that we spent a long time explaining in the talk. So without this definition of identity, this wouldn't be possible. So this is possible both because of the definition of identity and the univalence axiom. Yeah. So the culprits here are Voevodsky and Martin-Lev. So I find this very interesting, that there is an abstract notion of equality in a suitable foundation that actually allows you to formulate the univalence axiom and have these consequences. I can't say a lot more, but this could be a point to stop. So if I did stop here, what I would say as a summary is we define a general notion of identity. Well, not we, Martin Lev did. Vladimir Voevodsky gave an axiom for it, the Univalence Axiom, and from both the notion of this identity type and the Univalence Axiom, it follows automatically that equality of groups in the sense of the identity type is isomorphism, equality of topological spaces is homeomorphism. This is even more interesting because homeomorphism is defined in a way which is a little bit different from group isomorphism, because a homeomorphism is a bijection, is a continuous function with a continuous two-sided inverse, and now continuous as opposed to homomorphism. So when you define group homomorphism, you start from the source to the target, and you say the operations are preserved by the function. But when you say homeomorphism, you have to say continuous function, and continuous function is defined backwards, right? So inverse image of open set is open, and it doesn't matter. If you define topological space in the usual way and you write it down in the language of Martin Lev type theory, then you can prove that equality in the sense of Martin Lev's identity type is actually in bijection with a collection of homeomorphisms of these two spaces. And it's even more perhaps shocking that this also works with categories, because again, when you define, when you say when two categories should be considered to be the same, you could say that if there is an isomorphism between them, but category theorists know that actually isomorphism is not the right definition of sameness for categories. And so it's quite nice that if you define category in the language of type theory, then you can prove now that the type of identifications between two given categories is in bijection with the type of equivalences between these two categories. So I find this rather surprising. You have a single axiom, the Univalence Axiom, which makes that all notions of equality are as we expect. Yeah. So I have many more slides that actually try to explain the technical aspects of how this work, but probably this is a good time to stop. Thank you very much.
Thank you very much, Martin. So we now have some time for comments, questions. Valeria?
So I think it's great, Martin. You're great with this business of showing where the magic is happening and where things are to be expected. But there's still some things that bother me. So let me try to explain. The first one is this business that type theory kind of via Curry-Howard and stuff like that would naturally give you a notion of identity in each object, whatever the objects were, right? So the fact that the reflexivity is like an identity is not so interesting. The thing that's interesting is this idea that Voevodsky could think of other notions of equality, right? The business of deforming the paths or whatever. That this was also an example of Martin Lev's notion of equality. Is that correct, or am I kind of misunderstanding things?
So Martin Lev notion of equality is given by this. And sometimes people consider another axiom, let's call them 4 and 4 prime. So one was called the very uninspiring axiom was called the Streihes K Axiom. You can ask why it's called K. Well, because it's the letter after J. But the K axiom says the opposite of univalence. The K axiom says that there is at most one identification between two elements. So essentially, the K axiom says that equality is truth valued. So it's either true or it isn't intuitively. Yeah. Of course, this uses a kind of classical logic, but so the K axiom and both axioms 4 and 4 prime are compatible with these 3 axioms. Yeah. And I think this is the one that goes against Curry-Howard, because in Curry-Howard you try to avoid using truth values and you use types rather than truth values. Yeah. And this is exactly what is happening. So I can quickly explain the univalence axiom to show this. So the univalence axiom says the following. If you have 2 types in the universe, and then you form the identity type according to the axiomatization we gave in the previous pages, and you consider the type of equivalences. So I would need to define what an equivalence is, but think for the moment, think bijections. Yeah, that's the best approximation. So the type, this is the type of bijections. The type of bijections. You have to be careful. You have to define this properly. So more precisely is the type of equivalences. You have to define this in a correct way, otherwise you get an axiom that is not valid in any model. So you define the type of bijections, and now there is an identity bijection given by the identity function, and then the data that it is a bijection. And now let's go back a few pages here. Look at the induction principle, at the recursion principle. The recursion principle says if you have data like this, okay, so now we take actually we take A to be this notion, to be the type of bijections, yeah? So given 2 things, you look at the type of all bijections. Okay, so now it says that there is a unique function that maps the reflexive identification. And now for A, so here we take, here we take the type of bijections, and here we take the identity bijection. So there is a function that maps the reflexive identification to the identity bijection. Yeah, does it make a little bit of sense?
Yes, it does.
So that comes from the definition of the identity type. So the univalence axiom says that this function itself is a bijection. So this is a bijection.
Right.
Technically, you have to say equivalence, but think bijection, because I don't have time to define equivalence properly. And this is the univalence axiom. The univalence axiom says this is a bijection. So when I said canonical map before, the canonical map is actually this map given by J. Yeah, so this is the map given by the recursion principle. So so the univalence axiom says that the identifications are in one-to-one correspondence with the bijection. So for each bijection, there is one identification in the identity type, a unique identification corresponding to it. So I think I'm not sure if I am answering the question as you intended, but in a way, univalence is more in the spirit of Curry-Howard than the alternative axiom that some people considered, which makes it very non-Curry Howard.
Now that's great. That's very good. But one more thing: if you were to give a longer talk, would you be able to explain how the J relates to inductions as we knew it before?
Yeah, so that would be more a talk in Martin-Lev type theory, which is possible. So in Martin-Lev type theory, whenever you define a type, you define the type formers. So in this case, the type former is the identity. And then you define introduction rules. In this case is this. And then you define elimination rules, which sometimes are called induction principles. And this always follows the same pattern for the natural numbers, for sigma, for all the types have this pattern that you have an introduction, you have a type former, and introduction and elimination rules. I don't know whether you're referring to this, but this follows this pattern of Martin-Lev type theory.
No, that's good. Yeah, thank you. That's very good.
Yeah. Yeah. So what is just to finish? Yeah. So if you don't add either 4 or 4 prime, the identity type becomes very weak because it is very underspecified. I would say it is not sufficiently specified. Lots of statements about it are independent and not provable or disprovable. So to make the identity type work, you need this one. And another thing is that the univalence axiom, if you choose the univalence axiom instead of K, then it is a kind of an extensionality axiom. And in fact, it was, so, you may know that Thomas Streicher and Martin Hofmann, they had a preliminary version or a restricted version of univalence back in the 1990s. And they actually called it type extensionality. And it implies function extensionality and propositional extensionality and all the other extensionality axioms we know. Yeah, so from these 2 points of view, the point of view that it is more like Curry Howard because it has the information rather than just a truth value, and because it's an extensionality axiom, it may be, at least by some people, to be considered more natural. And these people include myself.
Right. I mean, yeah, kind of. I always thought that that models that Streicher and Hoffman had were a little bit.
They are simplified, yeah. So
Yeah.
they consider groupoids, one groupoids rather than going all the way. But I should have said this in the talk. I'm sorry I didn't. But they were the precursors of what Voevodsky did. Yeah.
Mm-hmm. That's also helpful. Thank you.
Yeah.
So, any other question or comments? Jean-Yves?
Yes, can you hear me?
Yes, perfectly.
All right. So as far as I understand, this framework does not directly deal with equivalence between structures. Equivalence between structures, for example, in the sense of model theory, when we say that two structures are equivalent if they have a common expansion by definition up to isomorphism, which is very useful notion. And do you think that this framework can, at some point, deal with this notion of equivalence?
Well, I don't know much about this subject that you're talking about, but so univalent foundations is a little bit different from set theory, but the claim is that you can formalize exactly the same things that you can formalize in set theory. So from this point of view, I don't expect any difficulty. And I mean, I don't know whether people in the audience know or not, but there are lots of formalizations of mathematics in the computer, so computer verified mathematics. This is done in the Proof Assistant Coq in the project Unimath that has started, was started by Vladimir Voevodsky, but there is also done in Agda, and it was done also in Lin. And so a lot of mathematics has been formalized, very sophisticated. So I don't think it should be a difficulty, but because it's not my area, I don't know what would happen exactly when you formalize this. Maybe I can just expand a little bit more on this. So, for example, if you were to do certain branches of mathematics, it would be much easier to do. In particular, homotopy theory is, in a way, is much easier and more direct to do using homotopy type theory and univalent foundations. Some people have writing a book called Symmetry, which is about group theory. And also, in the particular case of group theory, you can have slickier ways of proving things than in set theory. But in general, if you take an arbitrary branch of mathematics like combinatorics or I don't know, usually the formalization in univalent mathematics will look very much like the formalization you would do in set theory. So it is because I don't know enough about this subject that you want to try to apply univalent type theory. Two, I don't know whether the formalization can end up looking exactly like in set theory, modulo, the different syntactic details which are not important, or maybe whether the notion of equivalence that is built in and behaves well is built in the identity type. It may simplify this, but in order to conjecture whether you would get a simplification or not, I would need to look at specific theorems one is thinking about. Sorry for the long answer.
Okay, thank you.
Any other questions or comments? Okay, so thank you very much again, Martin.
Thank you very much thank you for having me.